Hey, it's Linford here, and in today's video we're going to be talking about the properties of integer exponents. In particular, we're going to talk about what the properties are and how we can use them to simplify exponential expressions. All right, we're starting off by talking about exponents, and it's a good thing to remember. What is an exponent? Remember, an exponent is essentially repeated multiplication. That's what it means to take something when something has an exponent, or take something to a power. You just repeatedly multiply it by itself. So, for example, if I had 3 to the 5th, that's saying 3 times 3 times 3 times 3 times 3, whatever, 5 times. 3 times itself, 1, 2, 3, 4, 5 times. If I had 4 to the 4th, that says take 4 times 4 times 4 times 4. All right, pretty basic. And then if I took a variable, we can work with that too. X to the 7th, that means I want, all right, count with me, x times x times x times x times x times x times x. I got 7 x's there. That's what exponents imply, repeated multiplication. Knowing this is what's called expanded form. Knowing expanded form, knowing how to rewrite exponents as this repeated multiplication is going to help us when we need to come up with some different rules, okay? Starting off, we have the rule for the multiplication of like bases. The multiplication of like bases says that if you have a multiplication problem going on where you have the same base, but you might have them to different exponents, what it says is you keep the base and you can add their exponents together. For example, if I had x to the 7th times x to the 3rd, well, this is going to be x to the 10th. Again, I have the same bases, so we added their exponents to get 10. Now, sometimes students might ask, well, why is this the case? Why is it that we're adding the exponents when we multiply the bases? And putting it into expanded form is actually going to help us really see that. X to the 7th is 1, 2, 3, 4, 5, 6, 7. Here are 7 x's all being multiplied together. And then I'm also multiplying 1, 2, 3 x's for x cubed. Isn't this just essentially me multiplying together 10 x's? Yeah, that's essentially what it is. So, I mean, there's no difference between me saying multiply 7 x's and then 3 x's, or just multiply 10 x's, because that's how many I have. That's the idea with this, okay? So then if I look at the problem, x to the 4th times x to the 10th, that's a multiplication sign. This is going to be x to the 14th. And if I had, for example, 2 to the 3rd times 2 to the 14th, that is going to be 2 to the 17th. A lot of times in this section, we might be dealing with really large values. It's fine to leave a number to an exponent, because oftentimes, it might get like ridiculously large. Like you might have, I don't know, 5 to the 81st power, whatever. And you would just leave it like that. You don't actually need to type it in your calculator, because your calculator probably can't even, handle a value that large. Okay, we talked about the multiplication of like bases, but what about the division of like bases? What happens when we are dividing the same base, but they have different exponents? Why don't we try to put this in expanded form and see for ourselves what the rule is? I'm going to take the problem x to the 8th over x to the 5th. That means I have 1, 2, 3, 4, 5, 6, 7, 8. 8 x's on the top, and 1, 2, 3, 4, 5 x's on the bottom. Okay, since I have this division going on, and all of these are being multiplied together, what I'm going to do is I'm going to say I'm going to cancel out pairs of x's. I just canceled out 5 pairs of x's. More so, I should probably say I divided out 5 pairs of x's. Because x divided by x, that cancels out. It's just a 1. X divided by x again is just a 1. And same thing here, same thing here, same thing here. All of these get canceled out or divided out. And what we end up with is what's left over. X to the third. Oh, little shortcut here. It seems like I just subtracted these exponents. And that's actually what the property is. If you're dividing by the same base but different exponents, you can go ahead, keep the base, and just subtract the exponents. So if, for example, we had x to the 6 over x squared, that would be x to the 4. Or if we have, let's take a really large number, 100 to the 51st over 100 to the 48. That's going to be 100 to the, let's see, 51 minus 48 is 3. So that's 100 to the third power, okay? That's the idea with the division of like bases. You have to remember, though, that the bases are the same. Same base. This would not work if I had x to the 6th divided by y to the 4th. This would not be able to be simplified, okay? They have to have the same base. Now let's chat about the power rule. The power rule says when I take an exponent to another exponent, so if I had some expression, a to the m, and I took this whole thing and I raised it to another exponent. Let's give this a try by writing it in expanded form and seeing if we can actually come up with this rule. I have x cubed to the 4th power. Well, that just means take x cubed times x cubed times x cubed times x cubed. I could stop here and use my multiplication of like bases, but why not go ahead and let's just actually write everything out in expanded form. I got the 3x's there times the 3x's here times the 3x's for the third and the last 3x's. All right, put everything into expanded form. Wow, not 3 at the end there. X. There we go. Put everything into expanded form. Let's take a look and see how many x's am I multiplying together. Well, hopefully you said 12. I'm just multiplying 12 x's together. So this rule says if you have an exponential expression raised to another exponent, all you need to do is multiply the exponents together. So for example, if I was working with really large numbers like 8 to the 15th squared, I could say that's 8 to the 30th. Similarly, if I had x to the 7th to the 5th power, we'd say that's x to the 35th, because we're just going to multiply those exponents together. These are essentially the 3 main initial rules: the multiplication and division of like bases and the power rule. What we're going to do next is we want to take a look at the power of a product and the power of a quotient. We want to figure out, for the power of a product, if I took a times b and raised that to an exponent, how could I simplify that? What shortcut rule could I do? Because I don't want to write expanded form every time. And then the same thing for the power of a quotient. If we had two numbers being divided by each other raised to an exponent, what do we think a shortcut could be to actually help solve or simplify what these problems are? Because like I said before, I don't want to write it in expanded form every time. That's going to be way too tedious and way too much to do. Instead, let's come up with some shortcuts for this. I'm going to recommend that when you come up with a shortcut, start by taking an easy problem. Start by taking an easy problem. For example, here I'm working with power of a product. Let's take 4x cubed squared. What I want you to do is put that in expanded form and see if you can come up, once you get your final answer, see if you can come up with what that shortcut is supposed to be. And then for power of a quotient, go ahead and take an easy example and see if putting it into expanded form helps you see what that shortcut is, okay? I'm going to have us pause the video, take a minute, see if we can kind of derive what these properties are, and we'll come back and check them together. Okay, well, hopefully you had plenty of time to work on this, to give it a try, but we're going to come back together and we're going to try and figure out what these shortcuts are. So if I have 4x cubed squared, that says I want 4x cubed times 4x cubed. Well, isn't that just 4 squared times x cubed squared, or 4 squared x to the 6? Or I guess you could even say that's, if you want to be technical, that's 16x to the 6. Yeah, that's it. So how do we go about and interpret the final solution from this to be able to just go from the problem directly to that final solution and not have to write stuff out in expanded form? Well, hopefully you noticed this idea that we took this exponent of 2 and we applied it to the 4 and to the x. Okay? A lot of times students think of this like distribution. They think of it like the distributive property, but it's not the distributive property. I have to be very clear about this. We are not distributing this 2 through. This 2 is never distributed through. Instead, what we're going to say is it was applied. We applied the 2 to each of the different number and variables, okay? So we never actually distributed. You can think of it that way, though. You can think of it that way. So let's try another example. 2x to the second, whole thing to the 5th power. Well, that's 2 to the 5th times x to the 10th. That's it. 2 to the 5th times x to the 10th. And all we did was we took that 5, we applied it to the 2, and we applied it to the x squared. Our property says that you can take that exponent and apply it to everything in the parentheses. However, I will give you a word of caution. You have to apply the exponent to everything in the parentheses. Notice how I did it to the number and variable alike. So let's try one that has multiple stuff in the parentheses. 2x cubed y squared to the 4th power. Okay, this means I want 2 to the 4th power, x to the 12th power, and y to the 8th. I apply that 4 to each of them, okay? Nothing too crazy. Think of it like the distributive property if you'd like. Just know that it's not. And then we can go from there. Okay, now let's take a look at the power of a quotient property. With the challenge, or with the challenge of taking x over y whole quantity squared, we can say, well, that's just x over y times x over y, which is just x squared over y squared. Maybe we do have a similar shortcut here. Notice how we took this 2 and we applied it to the numerator and the denominator? Well, there you go. That's the property. If you take some kind of ratio or some type of fraction, a over b, and you raise that entire fraction or the entire ratio to an exponent, you can take that exponent to the numerator and the denominator. Okay, so let's go ahead and apply this rule, and let's see if we can solve a couple more, maybe a little more complicated problems. Let's try x squared over y to the 4th, and this whole thing to the 3rd power. Well, that's x to the 6th over y to the 12th. I applied the 3 to the x squared and to the y to the 4th. And let's try one more for good measure. 2x to the 6th over 3y to the 4th. This whole thing to the 5th power. So we're going to have to apply this in a couple different ways. First, we're going to apply it to the numerator. And that means I have to apply this 5 to everything in the numerator, number included. So I have 2 to the 5th, x to the 30 over 3 to the 5th, y to the 20. And there I go. That's going to be my final solution. I applied that exponent to each thing within the fraction there. Numbers and variables. So there we go. We're all set with these. Power of a product and power of a quotient. Now there are two more properties I want us to talk about, and these include the zero exponent and negative exponents. The zero exponent says, if you take some real number, if you pick b to be some real number, and b is not 0, so you pick some real number other than 0, then b to the 0 is 1. Everything to the 0 power is 1, except for 0, okay? So if I had 5 to the 0, that's 1. If I had 5x, that whole thing to the 0 power, that's 1. If I had x third to the 0 power, that's 1, and so on, okay? And then negative exponents. This one's a little weird, but I'll define it for you. If b is a real number such that b is not equal to 0, and n all right, let me decipher these symbols really quick for you. Remember that this is the symbol for the real numbers. This n right here is the symbol for the natural numbers, and this symbol right here is, it's the same thing, but it's the set, it's going to be the symbol for the set of the positive integers, or the natural numbers. So everything from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay? So it might help if I wrote down the natural numbers are the set of 1, 2, 3, 4, and so on. But we're going to include, you could include a 0. We're going to later on in the chapters, but you could go ahead right now too and include a 0. And then the same thing with z positive. I'll include 0, 1, 2, 3, 4, and so on, going up into infinity. Basically all of the positive whole numbers. So that's the set that we're working with here. So we're saying that if you pick some real number and then you pick some positive whole number, then b to the negative n power is the same as 1 over b to the n. And what this implies is if I took 5 to the negative 3 power, that's 1 over 5 to the third. If I took x to the negative 4, that's 1 over x to the fourth. Let's make them a little more complicated. What if I took 5x to the negative 3? This is going to be 5 over x to the third. It is not going to be 1 over 5x to the third. That is not the answer. The reason is, and we have to be careful, note that this negative 3 is only attached to the x. It's only working on the x. So that's why I move the x to the negative 3 on the bottom of the fraction bar. What about an example like this? 4 over x to the negative 2. Well, in this case, I leave the 4. It does not have a negative exponent. And I'm going to move the x squared to the top so it becomes positive. In this way, I'm going about and just moving stuff either above or below the fraction line. That's all negative exponents mean. They just say, hey, take whatever we're attached to and move it to the other side of the fraction line. We're going to use some of these ideas right now to quickly simplify some more complicated exponential expressions. What I like to do in this case is first, I don't want to work with negative exponents, so I want to move all of these around. So I'm going to take this and I'm going to go through each number and variable and determine if it needs to stay or move to the other side. So let's start with 2. 2 is going to stay. It does not have a negative exponent. Same thing with x cubed and y. 8's going to stay. X squared is going to stay. Y to the negative 5, that's going to come up here. That becomes y to the 5th. z to the ninth stays, and z to the negative 4 moves down. Take a look, see if it makes sense to you why we're moving some things, why we're not moving other ones. And then what we need to do is we're going to start combining some things and simplifying. So I have, let's see, where to begin. Why don't we start with the y's. That's a y to the first times y to the fifth. That's y to the sixths. Oops, I made a mistake here. That should be a positive. That's a z to the positive 4. My mistake. Let's combine these. I have z to the ninth and z to the fourth. That's z to the 13th. And then I have x cubed over x squared. That's x to the first on the top. And then I pretty much just I just simplified all of the variables, and now the numbers can be simplified too. 2 over 8 is 1 over 4. And there we go. I've just simplified this. All I did was 1, move the negatives, and then 2, combine. That's all. That's the big idea with this. But then let's take a look at this example where, of course, we're going to make things a little more difficult. Here, can I go right away and start moving stuff around? No, I actually can't do that. And the reason is because of the parentheses here. Think back to order of operations. I have these parentheses. I cannot go and start moving stuff around. I have to get rid of the parentheses first. So to do that, we're going to use our properties of applying this 3 to every one of these things. All right, let's try to make this as neat as possible. But I'm going to take 3 to the third. X to the third is x to the ninth. Y to the negative 3. Z to the negative 6. It's kind of like we're going around and distributing everything, kind of like that. Again, it's not distribution, but that's the central idea. All right, I think we're about there. Now that we got rid of the parentheses, these grouping symbols, we can go ahead and start moving stuff around. All right, so 3 to the third is 27, and that can stay. X to the ninth can stay. 4 squared is 16. X to the eighth can stay. These y's are going to switch, so y to the fourth is going to come up top, and y to the third is going to go down. Z to the eighth stays down, and z to the sixth comes down. And then let's see what we have. 27, 16. X to the 9 over x to the 8 is just x to the first on the top. Y to the fourth and y to the third is y to the first on the top. And z to the 14th on the bottom. And that should be it. The only other step we did first was clear parentheses. Once we cleared parentheses, we then moved negatives. And once we did that, we just simplified like normal. Okay, let's try another one. This one, actually not any more difficult than the other ones, and in fact, because we have multiple ways of going about solving this. I'm going to recommend one technique that I really like to do to solve this. I like to simplify the inside first. I think of this like order of operations. I'm going to go ahead and simplify the inside first of the parentheses. We couldn't do that before, right? There was actually nothing we could simplify inside of these ones, so that's why I applied the exponents and got rid of the parentheses. But in here, I have a whole expression that can actually be simplified. So I'm going to take 16, x to the fourth, a 12. I'm going to move the x to the third up. I'm going to move the y squared down. Oops, the y squared. I'm going to move the y to the 6 up. The z to the first stays, and the z to the third stays. So this should be what I get when I start moving some things around inside of the parentheses. So we'll go ahead and we'll simplify this. 12 and 16, let's see, that would be 4 over 3. X to the fourth and x to the third is x to the seventh. Y to the fourth. And then z over z cubed is z squared on the bottom to the negative 3. All right, did some full simplifying on the inside. And now what we have to do is we just have to apply the negative 3 to everything. So that's 4 to the negative 3, x to the negative 21, y to the negative 12, 3 to the negative 3, z to the negative 6. And since everything's negative, all I really have to do is just swap everything. 4 to the third, x to the 21st, y to the 12th, underneath 3 to the third, z to the 6th. And that's it. That's how I can go about solving this. That's the technique I recommend. It seems like students really like that the most because we start by simplifying the inside first. Then we get rid of the parentheses. So you'll see each of these 3 problems, I just kept adding a step beforehand. Now, this isn't the only way to go about this. You could have, to begin with, distributed this negative 3 to everything. I will warn you, it can get a little messy if you do that. I'm not going to show you just because I think you can probably figure that out for yourselves, but I will warn you, it does get a little messy. But if that's how you like to think about it, go for it. Go ahead and give it a try, okay? That's as far as the exploration I have for you today. It should be enough to get you started on the homework. If not, always feel free to send me an email if you're confused on anything. My email is Linford, that's KLINFORD @wccnet.edu. And until next time, take care.